This is the lecturette for section 19.3, which deals with free energy. And this lecturette includes most of the section, but not two subsections that deal with free energy and the equilibrium constant, which are in a separate lecturette. So recall from the previous section that we saw that reaction favorability overall is based on the second law of thermodynamics that says for a reaction to be favorable, or spontaneous, meaning it could spontaneously occur, delta S for the universe must be increased, must be positive. And that comes from the delta S of the system and also the delta S of the surroundings. And the delta S of the surroundings comes from the system either giving off heat or gaining heat from the system reacting. And so that means that the reaction overall favorability comes from delta S of the system. It's related to that, but it's also related to delta H of the system, because delta H of the system will influence the entropy of the surroundings. Delta S of the system influences delta S of the system itself. So those added together will yield the overall delta S of the universe. We have another more convenient way of putting these together, and that's using what's called Gibbs free energy. And the Gibbs equation, or sometimes called the Gibbs-Helmholtz equation, is that delta G, free energy is given the symbol G, is equal to delta H minus the temperature times the delta S. And both of these are for this, all of these are for the system. So that's of the chemical reaction happening. And so now we're not going to be figuring out delta S for the surroundings anymore. This equation takes everything into account and figures out whether or not reactions are overall favored. And when delta G is negative, the reaction is favored. And when delta G is positive, the reaction is disfavored. And so delta G will be our touchstone for whether or not reactions are favored thermodynamically or not. A word about standard states. As we go through, what we'll be seeing is sometimes we'll be using delta G, delta H, and delta S, and sometimes we're using them with the little knots on them. And the little knots mean those reactions are measured under standard states, and what we mean by that is that all gases are at 1 bar pressure, which is close to an atmosphere. The species are in their most stable states. So, for example, if you're reacting chlorine, you'd have to be reacting chlorine to gas, not Cl gas, if you were just talking about chlorine, because chlorine exists as a diatomic molecule. Or you'd have to know that that was a reactant not in its most stable state. And if you have solutions, they're at a concentration of 1 mole per liter. So those are the standard states that we use when we talk about things that measured at under standard conditions. Okay, so let's look at an example here. Let's calculate delta G0, that is the standard free energy change, for this reaction here, which is actually the reaction used to make iron out of iron ore in a smelter. And we are given the delta H of the reaction for the system and delta S for the system. Notice that the delta H is normally calculated in kilojoules per mole of reaction, and the delta S is in joules per Kelvin, so we're going to have to deal with that. So delta G0 is going to equal the delta H, and what I think I'll do is I'll change the delta S into kilojoules. So the delta H is going to be 468 kilojoules minus the temperature. We're going to do it at 25 degrees first, and then we'll do it at 1,000 degrees second. 25 degrees will be 298 Kelvin, temperature has to be in Kelvin, times the delta S, which is 0.561 kilojoules per Kelvin. So notice I've taken the joules per Kelvin and converted that into 0.561 kilojoules per Kelvin by dividing by 1,000 to get from joules to kilojoules. So this is at 25 degrees Celsius, and when we do that mathematically, we come up with 301 plus 301 kilojoules. And the fact that that's positive so the reaction is what we call reactant favored. And by reactant favored, we mean the reaction is not favored to make products. That is, these are more stable than these, and so the reaction is not favored to occur. So let's repeat the calculation at 1,000 degrees Celsius, which is, of course, 1,273 Kelvin. So if we do that again, delta H does not change, it's 468 kilojoules minus now 1,000, 273 Kelvin times 0.561 kilojoules per Kelvin. And when we calculate that out, that comes out to be minus 246 kilojoules. That's negative. So the reaction is now, at this higher temperature, product favored. And what that means is that if you wanted this reaction to go, you'd know you'd need to go to relatively high temperatures. 1,000 degrees Celsius it'll happen. Relatively low temperatures it won't happen. It's disfavored then. So we can determine whether or not the reaction is favored, and we can do so for different temperatures. Now let's look at enthalpy versus entropy control for these reactions. So we saw for this one at high temperatures, what we saw in the last example is that, well, let's do this. Now let's talk about control of chemical reactions as to whether or not they're going to be controlled overall by enthalpy or by entropy. The key is that delta G, the sign of delta G, is going to control whether a reaction is favored or not. If delta G is negative, then the reaction is favored, and if delta G is positive, the reaction is not favored to occur, to make products. And the idea is at high temperatures, T is large. And so when T is large, delta S has the more important role. So the key is entropy controls reactions at high temperatures. Likewise, at very low temperatures, if T is really small, this goes to essentially close to zero. And so at low temperatures, delta H controls the reactions. And so at low temperatures, enthalpy wins. At high temperatures, entropy wins. Sometimes in reactions they both favor the reaction, sometimes they both disfavor the reaction, but when they contradict each other, when a reaction has an enthalpy or an entropy that differ from their favorability, then entropy is more important at the high temperatures, enthalpy is more important at the low temperatures. So what we can do is we can make a box diagram for temperature domains and reaction favorability. We know that negative delta H favors reactions because that helps delta G be negative, and we also know that positive delta S favors reactions. So positive delta S favors reactions because the minus T delta S will then be negative, helping delta G be negative, and negative delta H will help delta G be negative, so that also favors reactions. So what happens is, in a case where delta S is positive and delta H is negative, the reaction is always favored. And by always we mean at all temperatures. When delta S is negative, that disfavors the reaction. And when delta H is positive, that disfavors the reaction. And in that case, the reaction is never favored. That means at no temperatures. Now let's think about when they disagree. So for delta S being positive, that favors the reaction. Delta S being negative disfavors the reaction. When delta H is positive, that disfavors the reaction. And delta H is negative, that favors the reaction. So if you think about a case here where delta S is positive and delta H is positive, and we're talking about this place here, what will happen is at high temperatures, delta S will be more important. At low temperatures, delta H will be more important. So at high temperatures, delta S is more important, and delta S favors the reaction. So at high temperatures, it's favored because delta S favors reactions, and delta S is more important at high temperatures. At low temperatures, delta H is more important. Delta H disfavors the reactions, and so the reaction is disfavored at low temperatures. Now let's look at the other case where delta H and delta S are both negative. At high temperatures, remember, at high temperatures, delta S is more important, and if delta S is more important and delta S disfavors the reaction is disfavored at that temperature. And if we think about low temperatures, at low temperatures, delta H is more important, and delta H favors the reaction, so there will be favored. So the key is to know entropy. Delta S is more important at high temperatures. Enthalpy, delta. Start over. So the key is to know that at high temperatures, entropy, delta S is more important, and at low temperatures, enthalpy, delta H is more important, and then to know whether or not the reaction is favored or not by each of those based on their signs. Okay, so let's take a look at our case for iron oxide reacting with carbon that we saw before. In this case, delta H is positive and delta S is positive. So delta H disfavors the reaction. And the way we say that is that the reaction is enthalpy disfavored. Delta S is positive, leading to an increase in entropy, and so that favors the reaction. And the way we say that is that it is entropy favored. In what temperature change will this reaction be favored? It will be high or will it be low? So we know that entropy is favoring the reaction. Entropy is more important at high temperatures. Therefore, the reaction will be favored at high temperatures. So that's because entropy favors the reaction and entropy wins at high temperatures. At what temperature? The way we know that is that we know delta G has to be less than 0. And the idea is that delta G0 is greater than 0 at low temperatures, and delta G0 is less than 0 at high temperatures. And we saw that when we did our calculations here. At low temperatures, 25 degrees, delta G was positive, a good deal, and at high temperatures, delta G was negative by a good deal. The key is, where does it switch over? Where does it switch over from being positive to negative? And that happens where delta G is equal to 0. So delta G 0 equals 0. That equals delta H 0 minus T delta S 0. And we can rearrange this equation if we know it's equal to 0. Delta T, solving for the temperature is going to equal delta H 0 over delta S 0. And if we put in our values here, we have 468 kilojoules divided by 0.561 kilojoules per Kelvin, and we'll end up with the temperature in kelvins, and that comes out to be 468 divided by 561, 834 Kelvin. So the reaction is favored above that temperature, and it's disfavored below that temperature. We can do this by looking at some free energy versus temperature curves, or actually it turns out they're straight lines and not really curves. And we're going to do that by choosing different reactions here. This is the one we were just looking at a second ago. So at 25 degrees, 298 Kelvin, we see that delta G is plus 300 kilojoules, as we saw before. What this will do is, as I change the temperature, notice on the bottom, it calculates the new delta G for that. And so what we can do is we can move this, calculate. When I calculate, it'll add another point. And what happens is, as delta G starts out positive, so it's disfavored because delta G is positive here, and as I increase the temperature, what happens is delta G becomes more and more, or becomes less and less positive, and that's because delta S is a positive number and the temperature is increasing, so that's decreasing the delta G. And eventually we cross over And our crossover point is the one we saw before, around 830 degrees. So I'm going to go past that a bit. So when you go past above 835 degrees, all of a sudden delta G is negative. And so what we have is we have a case where at low temperatures, delta G is positive, so the reaction is disfavored. At high temperatures, delta G is negative, so the reaction is favored. Let's look at a different example. Let's look at this example here. Now, delta S is negative and delta H is negative. So what we would expect is we would expect that at very low temperatures, delta H will win out and the reaction will be favored. So I'm going to move this to very low temperatures. So at very low temperatures, delta G is negative, and so the reaction is favored. But now as I go to higher temperatures, what happens is delta G becomes larger and larger. And the reason for that is that the entropy change disfavors the reaction because it's a negative entropy change. And so as the temperature goes up, entropy becomes more and more important. So this chemical system will, at higher temperatures, become unfavored. So at relatively high temperatures, the reaction is disfavored, whereas at low temperatures, it's favored. So at low temperatures, delta G is negative, it's favored. At high temperatures, delta G is positive, and it's disfavored. So not all reactions are favored at higher temperatures. Very often they're not. In some cases, such as this one, this one, delta S is negative and delta H is positive, and what will happen here is that delta G will be positive at all temperatures. So this is a chemical system where at no temperature will delta G be negative, so the reaction is always disfavored. In this case is one where delta S is positive and delta H is negative, and so in this case the reaction starts out exothermic and at low temperatures, and when you increase the temperature it becomes yet even more exothermic. So the reaction is exothermic in all places. Some of these numbers are just theoretically calculated. They're kind of silly because we're at 729 Kelvin and the water would boil. So you couldn't really do this reaction, but you can calculate what the delta G would be at that temperature. Okay, so that gives you an idea for free energy versus temperature curves. Next, let's talk a little bit about a real-world example. Catalytic converters are used in car engines. What happens is the car engines are very hot, and where the gasoline's exploding. And what can happen is nitrogen in the air, which is in the air that's in the cylinder, and the oxygen that's there, the oxygen is present to burn with the gasoline, but those can do a different reaction and make nitrogen oxide, which is one of the components of air pollution, of smog. And this reaction has a delta H that's positive and a delta S that's positive. So because of that, what happens is it's favored at high temperatures. And so what happens is in the car engine, this reaction can happen, whereas because the car engine's very hot inside where it's reacting, whereas at room temperature it's not. So this species is more favored at high temperatures because of our signs of delta H and delta S. And it's also less favored at low temperatures. And so what happens is in the car engine, you go ahead and make this, and then when it cools down, when that gas is coming in, going back out your tailpipe of the car, it should back react and make that. But the back reaction, which is two NOs, go to make N2 gas plus O2 gas, that's favored at low temperatures, which is the temperature that the gas is when it's coming out of your tailpipe. So this really shouldn't be a problem. You should make this inside the car engine. It gets made. It's a bad molecule. You don't want it in the air. But it should just go ahead and decompose back to nitrogen and oxygen when it comes out of the tailpipe. But the problem is that this reaction is really slow at low temperatures. So the reaction should do this, but it's very, very slow, so it doesn't happen fast. And so what we do is we use catalysts. A catalyst is something that speeds up chemical reactions. So the catalytic converter in your car, one of its main functions is to take these nitrogen oxides that get formed inside the engine and help them get back to become innocuous nitrogen and oxygen as they pass through when they're cool. Because otherwise, the nitrogen oxide would get trapped in that less stable state, even though it's low temperature, because the reaction's slow. Okay, the last part of this we're going to be doing, is looking at the use of delta G of formation, free energy of formation values, for calculating free energy changes for reactions. And that is not using the entropy and enthalpy changes for reactions, but just using a tabulated version for free energy. And these values are found in the same data tables you've been getting enthalpy and entropy values from. And so free energy values are here. Free energy of formation values are found in tables, and we're going to look at a reaction and using them. But just like delta H of formation values, enthalpy of formation values, the free energy of formation for a compound is the free energy change, the standard free energy change, to make 1 mole of that compound from its elements in their natural states. So the reaction for this is not surprising. The free energy change for a reaction, you idiot. So the equation for this is not surprising. The free energy change for a reaction is equal to the sum of the free energies of formation of the products minus the sum of the free energies of formation of the reactants. And notice that free energies of formation for elements in their natural states are 0, like we saw for enthalpy change. So here we have 1 mole of ethanol in the liquid state reacting with 3 moles of oxygen gas to make 2 moles of carbon dioxide gas plus 3 moles of liquid water. And so delta G for a reaction, delta 0 for a reaction, is going to equal the free energy change of the products added up. So it's going to be 2. Remember, you have to use the stoichiometric coefficient for each of the compounds. 2 times the free energy change for CO2, and that is on our table right here, minus 394.4 kilojoules, plus 3 times the free energy of formation for the liquid water. So it's 3 times minus 273.1 kilojoules. And that comprises the free energy of formation of the products. And now we subtract off the reactants. And so there's only 1 mole of the ethanol. And so it's minus 174.8 kilojoules. And then we have 3 moles of oxygen. So it's 3, but the free energy of formation for oxygen is 0 because it's an element in its natural state. If we do our math through that, we come out with minus 1,782.9 kilojoules, which means, not surprisingly, that reaction is highly thermodynamically favored. And that ends our lecturette for this portion of section 19.3.